In this video, we are going to look at linear regression. This is very likely to be a chapter that is going to be something you use in many other classes that you will encounter in your college career. We are going to be looking at data sets and trying to find relationships within the data sets. And in this case, in this chapter, we're going to try to find the best fit line to go through the data. In this case, there is a direct relationship between the data. Notice that as the values of X go up, so do the values of Y. And we're trying to find this best fit line using what we call a least square criteria. In the picture above, we have all of our data points, and you see some very small black lines, which are what you might call errors. They're called residuals, and they're the distances away each of those dots are from the regression line. Now, I say distances because distances are always positive, but the ones that are below the line, we say have negative residuals, and the ones that are above the line have positive residuals. And if we look at all those little distances, those black line segments, and we find the sum of the squares of all of their lengths, the least square regression line is going to be that line for which the sum of the squares is as small as it can be. So the regression line is the straight line that best fits the data set according to this least square criterion, and the regression equation is the equation of the regression line. Okay, I know I'm getting a little bit detailed here. Okay, not all data sets will be approximately linear. Okay, so what we do is we always plot the data first. When there doesn't seem to be a linear relationship, as we see in this picture here, we say there's little or no correlation. When a prediction is being made outside the bounds of the given data, we say the prediction is called extrapolated. We use a process called extrapolation. And values that are predicted among the given values amongst them are said to be interpolated. Now, let me take this picture that I have here and make it a whole lot bigger for you to see. Our data values in this problem kind of range between these two black dotted lines, between 1,000 and 2,500. That's the relevant range for interpolation. Any predictions we made within that interval are said to be interpolated. Notice that our line turns into a dotted line as we go to the upper right and lower left corners of the screen. Okay, in that case, we don't interpolate, we're trying to extrapolate. And when we extrapolate, we're going outside of our model, and that can sometimes cause some problems. Now, I've made up this next example myself to illustrate something. I went online and I found this graph dealing with the population of 3 major cities in the high desert, Victorville, Hesperia, and Apple Valley, from roughly the year 1990 through 2015. And I decided that we would focus on Hesperia because there's a pretty decent relationship between them, whereas Victorville has kind of a jagged relationship. So I've taken a dotted line and I've extended this out. Now, if I wanted to use data values amongst these data values within this range between those given years, that policy or that process would be known as interpolation. And to do that, I would take a particular year, let's say it's the year, well, let's go with this year right there, right around 2007, 2008. Now, if I wanted to know roughly what was the population back then in Apple Valley or Hesperia, sorry, I'd go up to the graph at that location and then to the left to get the prediction. Now that is known as interpolation. When I go off to the far right to start making predictions, that would be extrapolation. For example, we don't know what the future holds. We don't know if all of a sudden people are going to say enough of this hot weather and they start moving away from the high desert. or the big earthquake comes, then the San Andreas Fault, and people just go, I'm out of here, boom. Or maybe there's a big, huge tidal wave and it takes out all of Orange County and LA and San Diego County, and people just don't want to live there. So they move inland, and maybe they do move to the high desert area, and maybe that happens. The idea is we don't understand anything about the future. We can't make predictions too far outside of our model. Now, another thing that's kind of strange is if you backtrack this model into the past, notice how somewhere around 1955, it looks like the population is 0, but before that, notice how it looks like we have a negative population. That's not meaningful at all either. And so that shows you some of the problems that we have with a linear model and trying to extrapolate beyond where the data actually is. Now, I've got a fun little comic over 4 dozen husbands. Okay, better get a bulk rate on wedding cake. I know that's kind of cheesy here, but the title of the comic strip says My Hobby Extrapolating. I think it's just kind of cool, and it just kind of re-emphasizes what I was talking about with you a moment ago. Now, when you are dealing with these types of graphs, we have what are called influential observation points. They are points that, if removed, cause the regression line to change considerably. Usually this data value is separated in the x direction, left and right, from the other data values, and thus pulling the regression line toward it without being counteracted by the other data points. So I have a graph here, and you can see that there's 2 different lines. In the top left corner, we have what's called an influential observation point. It's a little bit off to the left of the rest of the data, and you can see what the line looks with that point included and how the slope totally changes when you remove that point. Okay, in this next picture, it says these potential influential observation points are separated horizontally from the rest. So these would be influential observation points on the right. Now, usually it's just a single value, and different textbook authors will disagree on whether you can have several points considered to be PIOs, or whether whether you need to have just a single point. And this chapter is about linear regression, but I just wanted to include this picture at the beginning before we really get involved to share with you about different types of regression. You can see that in the dotted line down below, I have a quadratic regression. So instead of fitting it with a line, you'd fit it with a parabola, a downward one. And we could also take these dots and fit it with an x cubed model, y equals x cubed of some sort. And the goal is to try and find the best fit for that data. But there's no substitute for actually looking at the data itself without the curves and saying what type of shape best would fit that data. Okay, let's dive into our first problem, and I'm going to ask you to pause the video and type these values into list 1 and list 2 on your calculator. I'll read this here. It says 10 Corvettes between 1 and 6 years old. All of our X values are in years. Were randomly selected from the classified ads of the Arizona Republic. The following data were obtained where X denotes the age in years and Y denotes the price in hundreds of dollars. Now, I like to always take a look at one of the data values and interpret what they mean. That first one there means I have a car that is 6 years old. Now, the price is not $270, it's 270 hundreds, which means put 2 more zeros on it, and the price on the car is $27,000. So it's sometimes good, especially when you have a unit such as hundreds of dollars, to have that involved in the problem here. Now, I've left some notes space on your notes to write down the process we're about to go to. So pause this video if you haven't done so. I want you to do this along with me because we're going to be taking this problem through a whole bunch of different parts, and you'll get very used to this problem over the course of the next half hour or 45 minutes of watching this video. So, okay, I'm going to go right now to our calculator. Let me switch screens to the calculator. And I've already got this data typed into my first two lists, as you have already done. Now, every time you do this, you're now going to hit your Stat button. You're going to go over to Calculate, and then we're going to go down to Choice 4. Now, there are different types of regression models. If we were to do quadratic regression or cubic regression or quartic regression, which is a 4th degree model, all those choices are here. And even choice 8, there's a different linear regression. But instead of the y equals mx plus b or ax plus b that we're used to in America, sometimes they put the y-intercept first, and then they have the slope after that, the slope being the number in front of the x. Now, you're probably more familiar with choice 4 because you're used to this slope-intercept form that we use in America, but in other subject areas and in other countries, they tend to prefer choice 8 instead. I'm going to stick with choice 4. Now, when you choose choice 4, you're going to be asked to prompt where are your two data value lists. So I chose list 1 and list 2 by hitting my second L1 to type that in there. And this is going to be what's important. When you get down to the store regression equation portion here, you're going to want to follow the following keystrokes. Hit your vars variables button. Move one column to the right to y variables. Choose function, and then you can choose any of these, and I'm going to choose y1. What this is going to do is when it finds the regression equation, it's going to put it into the y equals menu, into the y1 function. Now, when I hit calculate, out come these values, which we'll talk about in a little bit. Now, some of you probably are finding out that you don't have r squared and r listed there. If that is the case, there are two ways to get those listed. And this is a one-time only calculation. You are going to hit the mode button. And if you happen to have all these different choices here, you want to make sure that your stat diagnostics are turned on. Okay, and then that's a one-time thing. Once it's on, you're good to go. Another way of doing this, and I'm going to quit out of here, is if you don't have that feature, you can hit second catalog, which has all of the menu items on your screen, and you can scroll all the way down until you find diagnostic on. It's quite a ways down here. And once you find diagnostic on, which is what I found right here, just hit enter a couple times, it will say done, and then your calculator will be able to go through and get those calculations. So again, you hit your stat button, you go over to calc, you go down to linear regression, ax plus b, choice 4, you tell it list 1, list 2, and then you do every time want to do this feature, because if you don't plug this regression line into this regression variable on your calculator, you may end up having the wrong line graphed on top of your data. So when you hit your variables button, one column to the right to y variables, hit choice 1 for function, y1 right there, hit calculate, and bada bing, out come these values. Now I'm going to come back to our other blue screen here now, and let's take a look at a couple of things. First off, here are the values that came out of the calculator that we will reference, and you're being asked to find the regression equation. Now, your regression equation is just this y equals ax plus b. So I'm just going to rewrite this here where my a is that value in front of X. Then my B is my y-intercept there, and there's my equation. Notice I wrote this as y hat. This is actually a sample regression line based upon our sample data. And we use a sample regression line to make a prediction about the population regression line. Now we will talk about the R squared and the R a little bit later. The next thing we would do is we would deal with the graph. Now, manually speaking, we'd have to draw our graph by hand, and that is just a skill from your algebra classes. I notice that my X values are all between 0 and 6, so I have my number line starting at 0 on the bottom left, going on up to 7 on the right. And then I looked at my Y values, and 405 is the largest, so I went up about 400, and I thought by hundreds, and I thought, let's put some truncation marks in there, and you could plot those point by point. But you also have a feature on your calculator that will graph this for you. So let me show you how to actually do that on your calculator. So here we are back at our calculator where we were. I want you to hit your y equals button. You will notice that that regression equation is already stored here because you told it to go into y1. Now let's go up into our stat plots. I'm going to hit second y equals, and I'm going to go into my first stat plot and turn it on. So I've got the flashing on button selected there. On the next row, that first choice is where we graph our XY data. And then in the two lines below it, I have list 1 and list 2 where my data is located. Now, when I hit zoom stat, zoom 9 is zoom stat, zoom 9, what it tells the calculator to do is graph your data and make it the window fit perfectly so that the data values fall right inside that screen. And then because we had that line stored to Y1, we can actually see that line drawn there. Now, what you might not know is that if you hit your trace button up here at the right, notice it will give you one of the blinking cursors there, and it says that's at 2,270. Now, if you hit left, it will move your cursor. Well, it won't go to the left. Let's try going up. Notice what it does is it's going to move you back and forth between different points on your graph, which I don't know that you need that very much, but it's just an option for you. I just thought I'd let you know about that. Okay, so let's go back here now to our problems and continue on. Anytime you are finding the predictor and response variables, those are basically just the X and Y variables. So for this problem, the age of the Corvettes and then the value or price of the Corvettes would be the predictor and response variables. As far as the outliers and potential influential observation points, I'm going to say none to both. Outliers would be a point up in the top right or down in the bottom left that's separated vertically from the other data values, and there just don't appear to be any on this problem. And potential influential observation points would be off to the far left or off to the far right, and there really aren't any that seem to be that far off. Yes, we have a gap in the middle, but there's 3 points to over at the left. So I'm going to say no to those values also. Now, when it comes to describing the apparent relationship between the age and price, that is not going to describe the slope, but it's describing this downward trend. I'm going to say as the age increases, the price or the value decreases. We say that there's an indirect relationship when your graph is going downward and one is increasing while the other is decreasing. And we say that there is a direct relationship when your line is going upward and both are either increasing or decreasing together. Okay, before we continue on with the next part of your notes, I'd like to do a matching exercise where I have 5 values of R and corresponding regression equations, and 5 different scatter plots. And our goal is to match up the 5 values of R, A, B, C, D, E, with the 5 scatter plots below. And you will notice that there are 3 graphs on the top that all have an upward trend, and the 2 on the bottom, numbers 4 and 5, tend to have a downward trend. So let's focus on that downward trend first, and that will be B and D, which both have the negative values of R. Now, the distinction between these 2 graphs is that second graph has this point in the top right corner. That is going to kind of mess up, so to speak. That's not the best words to use, but the chance for a perfectly straight downward regression line. So we're going to say that the value of R here is going to be the worst one, choice B. Whereas the negative 0.083, choice D, will be what we do here. And I think I skipped over a screen that I wanted to share with you. It's not right there. I think I am, well, we're going to do it anyways. We're going to say that when you have a line that goes perfectly through your data, whether it's going to be upward, that will be a +1 regression line. And when you have a line that goes perfectly through your data, but it's negative, that would be a -1 regression line. The one that's closest to the -1 is choice D. Now, when it comes to the next graphs, you can see that these 2 points that are up above the rest are going to be ones that are going to help us to make our decision on which value of R, the linear coefficient, matches the graph. And in scatter plot 3, you notice a vertical separation. Okay, and that's really going to mess it up. So it's going to have the lowest value of the remaining choices, which will be E, a 0.41, and these other 2 graphs are both about the same, except we have this point in the top right corner, which is going to be called a potential influential observation point in a moment, but that actually makes the regression line closer to +1, and so that would be C, and this one here would be A. Now let's talk about what we're seeing here. We're going to begin with this first one here. This point we said is vertically separated from the others, so that would be considered an outlier. Whereas on part scatter plot 2, that would be a potential influential observation point because it's separated horizontally from the rest of the data, and that's what makes it a potential influential observation point. Now, on the graph number 5, that point is actually kind of a little bit of both, but it's not so far off to the right. It's definitely an outlier, and an argument can be made that if you take that out of the regression line will be a lot steeper downward without it. So it's a little bit of a PIO, but mainly an outlier for this problem. Okay, so I wanted to kind of talk about this PIO and this outlier concept in an example after having gone through and talked about it here in part D. Okay, continuing on, we have a slope of our regression line, and I've rewritten it here. It came out. We know from our algebra classes when we have y equals mx plus b, that the m, the number in front of the x, is the slope. And we're being asked to interpret this in words. Now, I've developed some boilerplate language for you that you don't have to use, but it helps you when you're trying to do this interpreting. So I've said for every 1 x unit increase in the x variable. Well, let's take a look here. For every 1 x unit, my x unit was years old the Corvettes were. Increase is a default word in the x variable in the age, okay? The y variable, that's the price, decreases. Our slope is negative, so it decreases by about 20, instead of going 27.9029, $100, again, here's another place where it's easier to just move that decimal point over and write it as $2,790.29. Now, let's take another look at this sentence in a different way. You might remember from an algebra class, a slope can be considered to be a rise over a run. Any good description of the slope is going to have a rise and a run in it. And the first half of this sentence here is actually the run. Okay, our graph had age going horizontally, and as we had each one increase going from left to right, the price, the second half of this is going to be our rise. It's actually going downward, but it's a negative rise. And so we are describing the rise and the run here. Now, this language sometimes gets a little bit wonky, for lack of a better word, but it's pretty good boilerplate language that will work most of the time. Sometimes you can kind of reword it to make it make a little bit more sense to you. But this will be something that come your next test, you are going to be writing out for me that description in words, and it will not be a multiple choice offering. Okay, then part G now asks us to use the regression equation to predict the price of a 2-year-old Corvette. Now, there's two ways to do this. One way is to stick that number 2 into the equation, y equals mx plus b, just like in an XY chart on an algebra class. And if you do that, you end up getting 38.0979612, but you have to take into account that y is measured in hundreds of dollars. So you need to move that point over a decimal point over a couple of places so that you can write that as 38,079. Now I just said 38,000. Let's take a look here. Our units are in hundreds of dollars, and I think my mistake here was I put the decimal in the wrong place. This should have been 380, not 38 point, because the answer we want is 38,000. Okay, how would we do this on our calculator? Let's go take a look at our calculator right now. I'm going to move over there, and we last left our calculator right here. If you would hit second and then calc, which is above trace, and then you choose the word value, now you can enter in 2 for the value there. And when you hit enter, it's going to do 2 things. On our graph, you're going to get a blinking cursor where that would be located on the regression line, as well as down in the bottom right corner, there's that output that we saw a moment ago. And you can see it's 380, and I made that little mistake over on the screen, which I corrected. But there is the graph done for you, so you don't have to manually go and substitute the value in. There's my 380, move the decimal over 2 places, you have $38,079.61 as the predicted price based upon the regression line. Now, it asks us to calculate the value of the residual. Here is that same graph we had a moment ago with the cursor located at the 2,380. Now 2,370 is going to be below that point. So since it's below, the residual, if I were to draw it in, would be this little line segment here. And the residual is going to be negative because it's below. Then I'm going to say how far apart is the 38,000 and the 37,000, and our answer is going to be, if I write down, well, let's do it here. Here's our 38,000 and here's our 37,000 right there, and do the subtraction. You're going to find out the value of the residual will be negative $1,079.61. Now, technically, we are using the formula y minus y hat, where the y value is the 370, and this is the regression equation for y hat. So that's why the value that came out of the regression equation is the second number, and we're going small minus big to get a negative value for the residual. Continuing on, now we're going to talk more about this r and the r squared, beginning with r squared, which is known as the coefficient of determination. And we already know there's a couple of ways of measuring error, and we've been talking about this model over here on the right, where you have all these little residuals drawn in, and we talked about finding the sum of their squares. That's known as the SSE, the error square. There is another way while, because it will make more sense in a little bit. But I'm going to tell you r squared always ranges between 0 and 1. Values near 0 indicate the regression equation is not very useful, and values near 1 say it's extremely useful. So what I have here is this picture here. R squared goes from 0 to 1. R squared is called the coefficient of determination, and R, which we looked at a little bit ago, is called the linear coefficient. And when we're dealing with this, we're talking about the usefulness of the equation when we look at our r squared value. 0 is not very useful, and on the other end of the continuum, a positive 1 is very useful. So usually I'm going to ask you, what is the value of r squared? And we've already calculated it. It came out for free when we found our regression equation. So our value of r squared is 0.9368 when we round to 4 decimal places. Notice the r squared is positive, even though r is negative, because a negative times a negative makes a positive. And state how useful it is. Now, 0.93, we look at where it is on the continuum, and it's pretty close to positive 1. So we are going to say, since r squared is close to 1, the regression equation is very useful for predicting the cost of Corvettes. This will be something you will be wording for me in words. It will not be multiple choice. So you need to give me a reason, such as it being close to 1 or not close to 1. And the regression equation is, and talk about the usefulness. Very useful, somewhat useful, mildly useful, or not useful might be the words you use for predicting the cost of the Corvettes. Now, what I would like to do is I'd like to do a little activity with you here. I'm giving you we're not going online with this, but I will be giving you the link to this online for one of your activities. And you will be doing some exploring based upon this, and you will be changing some of these values in here. So I want you to pay close attention to this as best as you possibly can. If we were to go online, you'd see we have a data set here. There are 20 datas in this data set if I hold this bar down, but this is just a snapshot here. And apparently it's a class set of data for the length of people's feet and their height. And I'm assuming that the length of the feet is in centimeters, so I wrote centimeters there, and that people's height were measured in inches. Because the way I look at it, if someone is 74 inches tall, that would be 6'2", and that seems reasonable. And if someone's 56 inches tall, that would be quite a bit shorter, because 5 feet is 60 inches, so that would be 4'8". So that makes sense. And I've never seen people with feet that are 32 inches long, so I'm sure they went with metric there. Now, when you go online yourself for your activity, you will see that they will tell you what the mean is for each of these variables, and they'll give you the scatter plot automatically. You'll be able to go in and type over some of these numbers and reset the graph, etc. Now, I want to present to you two different models. The first model in blue is a mean height type of graph. Okay, this is our graph using y bar as a prediction. And the second one is using a regression model, y hat. Now, let's pretend I was trying to predict your height and you are sitting in a classroom and I can't tell how tall you are. Everybody's sitting at the desk, you're all about the same height. If I'm using this first model in blue, y hat, I'm saying, I don't care how long your foot is. My guess for you is about 67 inches, 67.75 inches, 68 inches would be my guess for you, and you, and you, and you. And it doesn't matter how long your foot is. And you can see that we've got a lot of deviation away from that prediction line. Whereas you're still sitting down, but I ask you, how long is your foot in centimeters? You tell me, and that allows me to then make a prediction for you. That's this second model using the regression equation, and that model is y hat. Now you can see that these dots are closer to that line, and it's a better model for predicting. Now, what's nice about this online situation is with this applet you can go into is you are then able to take a look at what will the residuals look like. And they've actually, you can check a little box there and it will show you the residuals on the left and all the residuals on the right here. And you can see that there's far less error in the red model than there is in the blue model. The question is, how much less error? How much did we reduce the error? Well, that's what R squared is. And here's that paragraph that we skipped over a little bit ago in our notes. R squared is a descriptive measure of the utility, of the usefulness of the regression equation for making predictions. Okay, it talks about how useful. How useful? Let's see. It is the percentage reduction obtained in the total squared error by using the regression equation y hat, using the red one, instead of the sample mean y bar, that's the blue one, to predict the observed y values. It's the percentage reduction obtained. It's a percentage. Percentages are between 0 and 100%. That's why R squared goes from 0 to 1. Now, in this particular problem, I'm going to tell you that R squared was 0.5. We've lost about half of the error. We've reduced it in half. But technically, it says it's the total squared error. That's a little bit different. I've clicked a little box that allows me to see all of the areas of those squares that have the residual as a side of the squares. And we have a lot of overlapping squares in each of these two pictures, and we're taking the sum of those areas, the sum of the squares of the residuals, and we're really looking at, when we look at all the areas in blue and all the sum of the area in red, what was the percentage reduction in the area? That's the total squared area, the total squared error. Now that's a little bit weird here because our brain thinks in terms of these lines, even though the calculation is being done here. So if I go back to our problem that we just did a little bit ago, and we said, oh, 93% of the error was reduced by going with y hat instead of y bar on this problem. And that's why it's very useful. When you have an R squared value of 1, that means 100% of the error has been reduced. When you have an R squared value of 0, that means none of the error has been reduced. Okay, so that's why it ranges from 0 to 1. And I wanted to explain that paragraph a little bit ago better using this activity. And you will be going online. I'll give you that link to be able to go and play around with those values, and you'll see the assignment that goes along with it. Now, when I continue along here, now let's talk more about this value of R. R is the linear coefficient, and it goes from -1 to +1. And these sentences I have drawn over here in the picture at the right. When you have a -1, there's a strong negative linear correlation. A perfect -1, as I said earlier, has a downward trend and the line goes perfectly through the dots. When you have a perfect +1, the line is going upward and it goes perfectly through the dots. So the slope of the line, if the slope is positive, your R value will be positive. If your slope is negative, your R value will be negative. Now, when you have a no correlation or zero, there's two ways of looking at it. You either have all over the place that really don't have a positive or a negative trend, or horizontal correlation, as I've got illustrated down below here. Back to our Corvette problem, it says compute the value of R. Well, you've already done that. It came out as -0.9679, which is pretty darn close to this -1 on the left end of this continuum. So in part L, when I ask you to interpret this, you will be doing this in words also. It will not be multiple choice. We're going to say, since R is close to -1, there is a strong negative linear relationship between the age and value of Corvettes. Now, typically for me, this is like a 4-point problem. Each of these underlined words, if it's missed, would lose you 1 point. Now, you might change your adjective a little bit, but negative and linear are pretty much fixed. And then the other half a point would go for the reason, and the other half a point would be what the relationship is between. So this will be something you will be describing in words. Okay. Now let's continue on and do a little bit more with this value of R. I have a guessing game based upon the value of R. And after I've done the first few of these, I'm going to encourage you to pause the video and start making guesses on your own, because it kind of is a fun little game. So here we go. I'm going to start with this first picture. There's definitely a downward trend. If I were to grab my drawing tool here and pick up a line, you could see that there is a line that would go right through that data like that, and you know that it's negative, for sure. So we are going to say that this is going to have a negative value of R, and it's close to -1. So I'm going to tell you it's -0.942. In the second picture here, oh boy, the points are all over the place. It looks like there's generally an upward trend, but I'm wrong. It's not very useful at all. This is pretty close to 0. This is like someone sneezed on the graph and there's those points. We can't tell an upward or a downward trend at all. These are very hard to predict. This next one, another one, very hard to predict. This one's even closer to 0, but it's positive instead, 0.007. I'd never have you predict those. Okay, as far as the next one, you can tell that there's an upward trend to this data. So you know it's a positive value, but it's not super, 0.274. We're really looking at how closely clustered the points would be around a line, and they're not super closely clustered as they are in that first graph. You do know it's positive, but not much more beyond that. Let's do one more together. Again, an upward trend. It's a little bit more definitive than the one before it, and so this will be a higher value of R. And it's about 3/4, 0.754. So for each of these next 6, I'm going to challenge you to pause the video and just kind of play a game with yourself. This is what we'd be doing if we were live in the classroom, making some predictions and seeing how good we are. And if you make a game out of it, it's kind of fun. So here we go. Let's take a look here. And this next one, oh gosh, you can see that one is definitely an upward trend. I should probably be quiet. I should have you pause this right now. But when you unfreeze it, definitely an upward trend, almost a perfect straight line upward. So this is going to be even closer to a positive one than that first graph was to a negative one. It turns out that that's positive 0.982 for the value of R. Okay, let me give you some of these other pictures here and have you take some guesses on these. We'll work at these a little bit at a time and pause this, make some guesses, or if you want, we can unveil these one at a time. Okay, this first one has definitely a downward trend to it, but the points are not super closely clustered around the line. It's kind of close to the here, and it's going to be negative. So I'm thinking negative somewhere in that same zone, so negative 0.667. This next one, we can see that there's an upward trend to it. That was not a very good drawing. Let me delete it. Let me try this instead, is a little bit better. And again, it's kind of around that 0.75. You can't tell much more beyond it, and 0.667. So it's almost like we're taking how closely clustered the previous graph is, kind of just changing the tilt, and that's what we have on this next one. The next one beyond this on the bottom row, number 3, has a downward trend. You know it's a negative, and it's not quite as close to -1 as that first graph is, but it's a little bit better than this one that's on the bottom left corner. So negative 0.891. And so hopefully you're enjoying this as a guessing game at home here. I'm just going to tell you the next one, positive 0.6. Very close to the one that was a couple graphs before it. The next one's kind of a smattering. You can tell it's positive, but not too much more. So just about 0.5, 0.496. And the one after that, 0.831. Now this is not the place to take the screenshot, because on the next screen, I have arranged these in order for you so that at the top left, we've got -1, and then they start getting bigger and bigger and bigger until we get up to 0. And then it changes to positive, and then it continues on the next row until you get to a +1. So all these previous graphs we did on the previous screen are now arranged in numerical order. And what I've done beneath them is I've put some words in describing them. We have a strong negative correlation on these first few pictures. Then it moves to a moderate negative. In the center, closer to 0, little or no correlation. Once it becomes positive, I have a mild or weak positive regression line. And then after that, it becomes moderately positive, and then somewhat strong, and then later, a strong positive correlation. This is a great place to take a screenshot that will help you as a study tool of identifying what the values of R are, but it also will help you with the adjective that you use to describe the linear coefficient. If I go back a few screens here, notice how I had asked you, there is a strong negative linear product. This is the adjective that you're going to possibly need to replace if the regression line doesn't have, isn't so close to +1 or -1 as this one is. So look at these words I have in green and pink, and that will help you to choose an adjective. And these are only suggestions for the words. This is a very fluid description. We just don't want you saying super strong when it's weak, and vice versa. Okay, continuing on here, we're going to do a little bit of a regression analysis here before we finish this first video. And basically, we have a few assumptions when we're doing regression analysis. We are assuming that the data is as closely clustered to the line as possible. And so I've kind of made a 3D model here of the regression line. And we want most of the data values to fall within a certain band. We've got a standard deviation type of graph drawn here. And we're saying for any specific value of the variable X, in our case, age of these Corvettes, the value of the dependent variable Y y must be normally distributed about the regression line. You want them to be closely clustered and not as many further away. Second, the standard deviation must be the same in each of these pictures. That's why each of those little normal curves I've drawn need to have about the same height and width in them. Okay, what we do when we're checking a residual analysis and how good our assumptions are for making predictions, we really want to look for what's called a residual plot. In particular, we want to make sure that there's no obvious patterns in it. We must not have any outliers, and the vertical spread must be roughly the same across the plot. So I've got a few different residual plots here, and it says for each of these following, determine whether the assumptions are satisfied. Well, here out, we have what's called a megaphone sort of effect, where they're closely clustered on the left end, but then they spread out over to the right. Okay, so that violates a couple. First off, it violates number 3 for the most part. And there is in number 1 above the first bullet, there is a pattern. It's getting wider. The next here is not evenly distributed here, and there is a pattern. So I'm going to say number 1 is violated because VIO, because there is a pattern involved. But what we really would prefer is this one here. This is a good model here, and the assumptions are met here because there's no obvious pattern, there are no outliers in particular, and the spread is pretty much about the same going across. They're all between those two values there. So that's what we are checking when we are trying to have good residual models, the residual plot. Now, how do you create a residual plot on your calculator? Well, here we go. I'm going to show you. We're going to go right back into what we did previously, but basically we're going to change out the y-list for residuals. Now, let's take a look on our calculator. I'm going to hit second y equals. I'm going to go into my first stat plot, and then down for my y list right here, I'm going to change out that y list for residuals. You may say, I never created a list for residuals, but the calculator did it for you automatically when you actually found that regression equation. It's automatically done for you. So you are going to hit second list, and you're going to scroll through your list. I'm going to go up from the bottom of mine, and there's my list called residuals. When I hit enter, okay, now that word residual is there, and now I'm going to hit zoom 9. And now you can see my residual plot that corresponds to this particular problem, which we could then do some analysis on. So I'm going to bring that back to our blue screen here, make it a little bit larger. Now, it's a little harder to do a residual plot analysis when you don't have many data values, but I don't see an obvious pattern. I don't see a megaphone effect. They do seem to be roughly evenly distributed above and below the line. So I'm going to say this problem, the assumptions were met as far as that process was concerned. Now, I'm going to stop this video. We have not finished this unit, but I'm just trying to break it down into 2 parts, and we'll continue in with another example and some other details in a little bit in the next video.